Lewis electron dot structures and formal charge. This molecule is formic acid. If we were to draw its skeleton structure, it looks like this. Notice that these two oxygens are very different. So if we were to draw Lewis dot structures, here's two possibilities to get that octet on that central carbon atom. We could have a double bond here, or we could have a double bond here. And that's what we're showing with both Lewis dot structures here. Notice that these are not resonance structures because these structures are not identical through symmetry. And the reason why is because double and triple bonds are shorter in length than single bonds. So these two structures are not identical. But which Lewis dot structure is the best? What we're going to do is calculate formal charge. And if we have all zeros, we have the best answer we can get regarding Lewis dot structures. So we can see here, we have all zeros for every single atom. So this is the best Lewis dot structure for formic acid. So what we are really doing is calculating the Lewis dot structure that's the lowest in energy. And that is always the most stable and how a molecule exists in nature. Using formal charges to select the best Lewis structure. Now before we get into how to calculate a formal charge, let's just go ahead and remind ourselves how to write a Lewis structure. So let's write the Lewis structure for phosphoric acid using this below skeleton structure. So we know that we have 3 hydrogens, they're 1 each. We have a phosphorus, and phosphorus has 5 valence electrons. Oxygen 6, so plus 5 plus 4 times 6. That gives us 32 valence electrons. So let's go ahead and make our covalent bonds and make octets on everything. And if we have anything left over, we'll put it on that phosphorus atom. Now maybe we need too many electrons. Let's find out. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I've used up all of my valence electrons. I don't see anything wrong. Everything seems to have an octet. But is it the best structure? Let's calculate formal charges and find out. So here's the equation to calculate a formal charge for any atom. All we do is take its number of valence electrons from the periodic table, subtract the number of bonds with that atom that's in our Lewis dot structure, and then if that atom has any lone electrons, we also subtract that number. So let's try it. Let's check out hydrogen. We'd have 1 valence electron minus 1 bond minus 0 electrons, we have 0. So all these hydrogens with just 1 bond has a formal charge of 0. That looks great. Let's check out this oxygen. We have 6 valence minus 2 bonds minus 4 lone electrons, 0. Looks great. So all of these are 0 too. How about this oxygen? We have 6 valence minus 1 bond minus 6 lone electrons. It's a -1. So this is a -1 formal charge. How about that phosphorus? The phosphorus is 5 valence minus 4 bonds minus no lone electrons, +1. So notice a few things here. If you do everything correctly, all of the formal charges add up to be the overall charge on this molecule. Well, this molecule doesn't have a charge, so all of our formal charges should add up to be 0. So we have zeros for everything except phosphorus and oxygen. So if we can come up with a Lewis dot structure that has zeros for everything, that would be the best Lewis dot structure that we could get for this molecule because it has an overall charge of 0. So since this oxygen has a non-zero formal charge, let's move those electrons in there and make a double bond and see what would happen. So our structure looks like this. Can't change our skeleton. And all we did is we made a double bond here by moving those electrons in. Everything else is going to be the same. So now let's recalculate those formal charges. For this oxygen, we'd have 6 minus 2 bonds minus 4 lone electrons. We got 0. For the phosphorus, 5 valence electrons minus 5 bonds, no lone electrons, 0. So we got 0 for everything. This is the best answer. That's the best Lewis dot structure that we can draw. Now here's some suggestions with formal charges. Always choose a Lewis structure with all formal charges as close to 0 as possible. Sometimes you may not get all zeros. The sum of all formal charges equals the overall charge of the structure. So if we have sulfate, for example, if you add up all the formal charges of a sulfur atom and its surrounding 4 oxygens, you will get a -2 for the sum of all the formal charges. You can't get all zeros. It's not possible. A negative formal charge should be on the most electronegative atom in the structure. So we already found the best Lewis dot structure for phosphoric acid. Found it up here. Okay, one more topic. Let's calculate the enthalpy of a reaction. Remember that's symbol delta H subscript RXN, using tables of bond energies. We already have multiple ways to get the enthalpy of a reaction. This is just one more way. The enthalpy of any reaction, all we do is find the sum of all the bonds that are broken, add up all those energies, then subtract out the sum of all the bond energies that are forming. And the idea here is that this is positive energy. You have to put energy in to break these bonds. When a bond is formed, that's energy given off. So that's negative. So pretty much that's all we're doing, is we're breaking up some bonds and we're forming others and just keeping track of the energy. So let's use bond energies to determine the enthalpy of this below gaseous reaction. So my enthalpy of reaction I'm going to break these bonds. I'm going to form these bonds. And what I would like to do, so I don't mess up, is I just pretty much break everything. And then I'm going to form everything. So what bonds am I going to break? Well, I have 1, 2, 3, 4 carbon-hydrogen bonds. So a carbon-hydrogen bond is 411. And I'm going to break that carbon double bond, that's 602. And I need to break this hydrogen bond, HH. That's 432. Now I'm going to form all these bonds. What bonds am I going to form? Well, I'm forming 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. Carbon-hydrogen is 411. And I'm forming this carbon-carbon bond. That's 346. So I would take 4 times 411 plus 602 plus 432. It equals, subtract out, parentheses, 6 times 411 plus 346, close parentheses. Get about a -134. And my units are kilojoules per mole. So it's kind of an easy way to get the enthalpy of a reaction, as long as you have the tables. Okay, so let's get back to writing Lewis structures. So write the best Lewis structure for each molecule and clearly indicate the formal charge for each atom. Start with the valence. We have 6 for oxygen, plus 6 for sulfur, plus 2 times 7 for fluorine. So I have 26 total valence electrons. So if I connect everything, make octets on all the surrounding atoms. Anything left over, I'll put on the center atom. Let's see if I used too many here. So I have 8 times 3 is 24. 2 more, make it 30. If I calculate my formal charges for the fluorines, 7 valence minus 1 bond minus 6 electrons, it's 0. So these fluorines are 0. Looks good so far. For this sulfur, I have 6 valence minus 3 bonds minus 2 lone electrons. I have a positive 1. And for this oxygen, 6 valence minus 1 bond minus 6 lone electrons, negative 1. So I can do better. So what we'll do is make a double bond between the oxygen and the sulfur. Let's move these electrons in and see if that will improve our formal charges. It's my skeleton. So what I did is I made a double bond. Leaving the lone pairs on the fluorines alone, because I had good formal charges there. So my fluorine's already calculated. I have zeros on those. Those look great. Let's check out this oxygen. Did it change? I have 6 valence minus 2 bonds minus 4 lone electrons, 0. Great. How about that sulfur atom? 6 valence minus 4 bonds minus 2 lone electrons, 0. So everything is 0. There's my best structure. How about bromate? Bromine has to be in the center, surrounded by 3 oxygens. I have 3 oxygens, so 3 times 6, plus 7 for bromine, plus 1 for the extra negative charge. We end up with 26 valence electrons. So if I make octets on the surrounding oxygens, I have 3 oxygens, each one has 8, so that's 24. I have 2 more, there's 26. So is that my best structure? So these oxygens, I have 6 valence minus 1 bond minus 6 lone electrons, a negative 1. So on these oxygens, I have a negative 1 formal charge on each one. On the bromine, 7 valence minus 3 bonds minus 2 lone electrons, the positive 2. So if I add up all my formal charges, I have 3 negative 1s, so that's a negative 3, and a positive 2, and I get a negative 1 overall formal charge. So that looks great. That's how it should be. However, can I get all zeros and maybe 1 negative 1? Can I reduce? Let's copy what we have. So I'm just going to copy this structure and see what my choices are. So this is our structure. What if I took some of these lone electrons and moved them in there? What would happen? Now here, I would have 6 valence minus 2 bonds minus 4 lone electrons. I get 0. So why don't we move all of these in? And we'll have zeros on all those oxygens. Let's try it. What would that look like? Put a double bond here. Put a double bond here. And our formal charges are zeros for those oxygens. What is it for bromine? We have 7 valence minus 6 bonds minus 2 lone electrons. It's a -1. So this is the best structure we can come up with because we have all zeros for formal charges except for bromine, which is a -1. All right, so try these and see if you get the same answers that I get. Let's count up the valence. I've got 5 for nitrogen, 7 for chlorine, and 2 oxygens. 2 times 6, total 24 valence electron. So if I make octets on these 3 surrounding atoms, I'll have 24 electrons used up already. So I won't have any lone pairs on that chlorine. So I've used up all 24 electrons. Let's try calculating formal charge. These oxygens, 6 valence minus 1 bond minus 6 lone electrons, it's a -1. So this oxygen's a -1 also then. On my nitrogen here, I have 5 valence minus 1 bond minus 6 electrons. It's going to be a -2. So this chlorine is going to turn out to be what? I'm going to have 7 valence minus 3 bonds minus 0, +4. So if I add up all of my formal charges, I get 0. So that's looking correct mathematically. However, I have some really big formal charges. So let's see if we can fix things here. Let's move these in and make double bonds, because that'll make those oxygens 0. Then let's move one of these in and make a double bond. See if that will help. So now I have a double bond here, a double bond here, and a double bond here. Let's recalculate these formal charges. Let's see if we get this to work better now. Here, 6 valence minus 2 bonds minus 4 lone electrons, 0. Great. So this one is 0 also. My nitrogen is going to be 5 valence minus 2 bonds minus 4 lone electrons, -1. My chlorine, 7 valence minus 6 bonds, +1. So it's getting better, but this is a neutral molecule. Can I get all zeros? That's the best possible answer. Let's try moving this lone pair in and making another bond and see what happens. When I do that, now I have a triple bond there. And I need to recalculate my formal charges. Now for nitrogen, I have 5 valence minus 3 bonds minus 2 lone electrons. I've got 0. This is looking better. Chlorine, I have 7 valence minus 7 bonds, no lone electrons. I get 0. So this is my best structure. Zeros on everything. A double bond with the oxygens and a triple bond with the nitrogen. It would be pretty difficult to figure that out without formal charges. Let's try this molecule. Let's count up the valence. 1 for hydrogen, 6 for oxygen, 7 for chlorine, and 6 for oxygen again. So that's a total of 20 valence electrons. So if we connect everything, make octets on the surrounding atoms, how many have I used up? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. If we calculate formal charges, 1 minus 1 minus 0, you get 0. That looks great. This oxygen, 6 valence minus 2 bonds minus 4 lone electrons, that's 0, so that looks good. How about my chlorine? 7 valence minus 2 bonds minus 4 lone electrons. That's a positive 1. And this oxygen hopefully will come out to be a negative 1. 6 valence minus 1 bond minus 6 lone electrons, negative 1. So let's see if we can improve that by moving in that double bond. So I would erase it, make a double bond, recalculate my formal charges now. This chlorine, I now have 7 valence minus 3 bonds minus 4 lone electrons, 0. Great. This oxygen, 6 valence minus 2 bonds minus 4 lone electrons, 0. Everything's 0. That's the best structure I can get for a neutral molecule. One more. Fluorine has 7, chlorine has 7, oxygen has 6. That's a total of 20 valence electrons. So if I make octets on the surrounding atoms, and anything left over I'll put on the center atom. So I've got 8 and 8 is 16, 18, 20. So with my formal charges, fluorine has 7 minus 1 bond minus 6 lone electrons, 0. Fluorine is happy. Chlorine, 7 valence minus 2 bonds minus 4 lone electrons, positive 1. And this oxygen, I bet will turn out to be a negative 1. I've got 6 valence minus 1 bond minus 6 lone electrons, a negative 1. So on a neutral molecule, all zeros is the best. So let's see if we can do that. Let's move that in and see what will happen to our formal charges. Now I have 7 valence minus 3 bonds minus 4 lone electrons, 0. Great. For oxygen, 6 valence minus 2 bonds minus 4 lone electrons, 0. Great. So the idea here in drawing the best Lewis dot structure for molecules is to use formal charge. We're not even using CNOS anymore. We use it as a guide, but no, formal charge rules the day. So to calculate the formal charge of any atom in your Lewis dot structure, take its number of valence electrons from the periodic table minus the number of bonds in that structure minus the number of lone electrons that atom has in that structure, and hopefully you'll get zeros for everything on neutral molecules, and your formal charges will add up to be the overall charge on charged molecules. Good luck.